And welcome back to the third day. And today we talk about exploring uncertainty and later on about also visualization, a lot of things related to the IPCC. And yeah, we're happy that Céline Guivarch accepted to also give a talk. She has been working a lot on IPCC and especially also the role of uncertainty in scenarios, etc. So yeah, so very happy that she accepted to give the talk. And so you have 1.5 hours. I think, yeah, if you have questions in the meantime, it's also, please just wait for the mic and then you can have comments and questions. And yeah, so Céline, floor is yours. Maybe a quick introduction. I think it's always nice. And yes.
Okay, sure. So someone wants to be admitted in the waiting room. Okay. Thank you very much for the invitation. I'm very happy to be here and then have the opportunity to meet you all. So I'm Céline Guivarch. I'm a researcher at CIRED, the International Research Center on Environment and Development that is based close to Paris. And well, I work on climate, mainly with models, mainly with IAM models, but not only. And I'm half an engineer and half an economist. Yeah, so I didn't know what to talk about, so I was a bit uncertain, and uncertainty was an easy one. So we'll talk about uncertainty and about exploring our uncertain future with IAMs and scenarios. Of course, my presentation will be illustrated by some academic research articles, but also by drawings from a graphic novel artist I like a lot, Marc-Antoine Mathieu, and all the drawings are from his book that is titled Sens. And so sens in French means both direction and meaning. And I think it fits well with what we're trying to do with IAMs and scenarios in a way. So exploring directions and trying to find meaning. So let's see if this works. Now it does. Let's start with some questions. So you probably, okay, you know WooClap. You can use the QR code or go to the site and use this code here, JBMYFX. And once you're there, I would like you to think about, yeah, probably your latest work, maybe the one you presented here in the poster, or maybe another one if you prefer. And let us know what uncertain factor had the most influence on your result. So you can either like some of the words that are already listed, like population, economic activity, climate change impacts, energy demand, technology parameters, or others. You can add some new words, and you can also like the new words that others would have added. And let's see if I manage, maybe you can help me to show the WooClap. Yes. Easy. Okay. So it seems that climate change impacts, technology parameters, model assumptions. Yeah, well, that's a very broad way of putting things. Our discount rate is also socioeconomic projections are important elements. It keeps moving. Okay. And maybe now we stop. and have a moving overview of what is the most important uncertain factors that we deal with. So yeah, it's still socioeconomic model assumption, climate change impact, technology parameters, fuel prices, discount rate, population a bit, energy demand a little bit. I have a second question, but I don't know how to advance. No, it's also on WooClap. Yeah, but I don't. Yeah, but I don't have it on my screen. So. Okay.
So this one on the right?
This okay. So yeah, my second question, and that will maybe go into the model assumption type of phrasing that you had. What type of uncertainty do you think dominates your result? Is it the uncertainty in the values of the input parameters that you use? Is it the uncertainty about the forms of the relationship that you represent? Is it the uncertainty due to mechanisms that occur in the real world, but that is emitted from the boundary of the system that you represent? Is it maybe some other type of uncertainty, or maybe you don't know? Okay. So there's it's still moving, but there's a clear and concerning picture that is emerging, that it seems that omitted mechanisms are the main type of uncertainty that dominates for what we're doing. So that's interesting. And it's, I mean, probably. But let's go now. Can you again help me? I'm sorry. I feel.
Forward, or?
Yes, can we go back to the presentation? So yeah, that was just a small warming up to maybe wake us all up. And now, yeah, fantastic. And now that's so, okay. So after this small warm up, here's what we'll try to do. So first I'll introduce some frameworks to think about uncertainty and modeling. Some frameworks that have influenced my own thinking and my research, and I hope can be useful to your own thinking. Then I'll detail a few case studies from some articles that I'm a co-author of, and that explore, in a way, uncertainty with some IAMs. Then I'll have a few concluding remarks. You'll see on the slides, like the reference of the articles are at the bottom every time. So in the case studies, there are articles that I'm a co-author of, so I know them well. Some are a bit older, so I might not remember all the tricky details, but also in the frameworks part and in the conclusive part, I do use some articles that I'm not an author of, but of course the reference are there. So yeah, you can find them easily. So yeah, well, first, I mean, from the start, models and IAMs in particular were built precisely to explore the future possible evolutions of the systems that we're looking at. So they were meant to explore uncertainty in a way, and with various methods that have been used, and now increasingly the model results are used in policy setting and policy evaluation, even in legal cases. So it makes the importance of uncertainty exploration and communication important, I think. So first, if we needed a motivation to study the uncertainty with IAMs, here is one. It shows the source of uncertainty in climate model results in terms of global mean temperature and the contribution of various sources of uncertainty. So in orange, the internal variability of the climate system, that is a chaotic system. So it's small and it matters only in the short term. Then you have in blue, the uncertainty and climate models and their structure. So that reflects our incomplete knowledge or our incomplete of the climate system itself. That is a bit bigger and also matters mainly in the short term. And then in green, you have the uncertainty from emission scenario uncertainty. So that's the uncertainty that we modelers making the emission scenarios are responsible for. And that's the dominating share. And so it's important that we characterize that uncertainty. And because we talk about uncertainty, I thought it was very important to situate us firmly in the post-normal science. So we are indeed in a case where some facts are uncertain. For instance, the climate damage or the future economic growth. Values are in dispute. For instance, not everyone agrees on which priorities should be given in human development policies. The stakes are high and decisions are urgent, and that suppose I don't need to convince you that it is urgent to act on climate change to avoid its worst impacts. So yeah, so we are really in that space. And so where before science was probably understood as advancing in the certainty of our knowledge and control of the world. And now science is probably seen as coping with the many uncertainties in policy issues of risk and of climate change in particular. And in that case, uncertainty cannot be banished or maybe reduced, but it has to be managed. And also values cannot be objectively defined or presupposed, but they are that we need to make them explicit. So on the types and sources of uncertainty, there's scientific uncertainty because our knowledge about the causes, processes, and consequences of a system evolution is incomplete, either because the processes that govern the system evolution are stochastic by nature, so the outcome is known in advance, like it's like rolling a dice, or because it varies depending on the context, and the context cannot be fully characterized. It can also be because our scientific knowledge is still limited because we lack observations and measurements, or because we have conflicting evidence or poor quality of data. And this can be improved over time with better data, better measurement, for instance. But it may also be practically, well, some things might not be practically measurable in some cases. And for instance, the economic damages from climate change are extremely hard to measure because we don't have a counterfactual without climate change to compare. So we need a model to actually do that. Then on the types of uncertainty, we can think of a gradual scale spectrum from determinism to total ignorance. So with 4 levels in between. The level 1 would be, we have a point estimate with some small range around it. The level 2 is that we're able to have a distribution of probability of the system output that is of interest. Level 3, we have a few alternative plausible evolutions in the system. Level 4, many plausible evolutions or even unknown evolution, but but we know we don't know. And I would say we're mainly at level 4 when we, for our work in general. For some others, maybe a bit to level 3 or maybe 2. And there's also total ignorance. So the unknown unknowns, the famous from the Donald Rumsfeld speech, yeah, for other things. So there are also different types, I would say, in that scientific uncertainty. One is really a risk type uncertainty. So that would be the probability type. It's when it's known and perceived as quantifiable uncertainty. We have an objective distribution of probabilities, either because we know a priori from a mathematical calculation, like when it's a lottery or rolling a dice, or because we can infer from a large number of observations or experiments, observation of a system evolution in the past, and we know the system would be stable over time, and we could use the frequency, the observed frequency, as the future probability for an event. Of course, because the climate is changing for everything about climate, we don't have that stable over time system, so we're usually not in that risk type uncertainty. There's also the uncertainty proper, so it's when we're unable to define like objective probabilistic distribution, or to describe the unknown, the known uncertainty in statistical terms. Yeah, so that is what I would call uncertainty proper, what economists would call probably ambiguity. Sometimes we even call deep uncertainty a situation where the analysts do not know, or the parties to a decision cannot agree upon the appropriate models to describe the interactions within the system of interest, or when the probability distribution to represent the uncertainty about some key parameters of the models are also not known or cannot be agreed upon, or if there's disagreement about the value, how to value the desirability of some alternative outcomes of the system evolution. And actually, in the definition of deep uncertainty, you could already see that it is not just about scientific uncertainty, but it's also about the disagreements about the values and desirability of outcome, and this relates to ethical uncertainty. So ethical uncertainty is when it's not clear what framework we should apply to value the outcomes and to address the ethical question raised by a given process of decision. And for climate change, for example, there's the question of the distribution of outcomes within a generation or between generations. So the intra and intergenerational equity issues that like imply using a discount rate, or deciding what inequality aversion or what risk aversion to use in the social decision, social choice framework that we use. And that is, I mean, an ethical decision per se, and there's no one right social choice framework or value of those parameters that are the ones to use. So if we come to decision making under uncertainty, so the uncertainty with respect to decision making is when there's a gap between the available knowledge and the knowledge that the decision makers would need in order to make the best, the optimal decision. What matters actually for decision is not only uncertainty, but also the question of irreversibility and inertia that the decision make. And there are some nice old papers by some very good economists that have highlighted that issue of the conjunction between uncertainty and irreversibility. That is the problem. And of course, because if you don't have inertia and irreversibility, your decision do not matter, because you can always change your decision over time and when you have new information. And indeed, we're often like in a case where it involves decisions that are made over time at several points in time and that interact with the system evolution. In that case, the decision may rely on frameworks of sequential decisions. So you take a decision, you learn new information, you revise your assessment, you take a new decision, etc. In that case, you can use things like the precautionary principle that sort of give more weight to trying to avoid the worst cases and leave open as much as possible the possibilities for future decisions. You might also want to use the idea that well, actually trying to optimize an expected result is probably not adequate, but it's rather about trying to minimize regret or to avoid creating some vulnerabilities. And one of the frameworks that is really trying to operationalize that idea of decision-making under deep uncertainty as robust decision-making, that was like Rob Lampert is one of the person who works with this framework a lot. So it's a framework that really takes very seriously that decisions can have very serious consequences if the decision makers think that the risks are well characterized, but it is not, and that we know uncertainties are always, well, almost always underestimated, and so it's a way to try to rethink how uncertainty is incorporated into analysis and into planning and decisions. So the method seeks to discover and characterize the cases in which a strategy, a decision is not effective, in order to improve the strategy and design one that is more robust to uncertainty. So in that case, models are used to generate many scenarios and to assess the performance of a proposed strategy in those many scenarios, to focus on the ones where the strategy is not effective, to try to understand why, to show that to the decision makers, and to iterate to improve the strategy until it's judged that it's robust, sufficiently robust to the uncertainties that are covered in the analysis. So now what this all means for modeling and modeling studies that are meant to inform decision-making under uncertainty. Well, we have to manage uncertainties in model quantities. So the parametric uncertainty, the alternative values to give to our parameters. We also have to consider uncertainties in the model form. So for example, the form of the damage function. So that's the structural uncertainty, the alternative function and relationships that we represent in our models. We have to also maybe be mindful of the uncertainties in the model completeness and adequacy. So that's the omitted mechanisms. For example, tipping points are often omitted from integrated assessment models, like the ones that look at damage. So that would also be structural uncertainty, I would say. And it might be important to focus on salient uncertainties that would be both what is thought to be uncertain, so that is the object of scientific controversies, so that needs to analyze the state of knowledge, and also what matters for the model result. So it means that we need to have also some analysis of the model sensitivity. And when we have both, those are salient uncertainties. So since we're talking about modeling, let me very briefly introduce the IAM that we are working with at CIRED, and which will be used in some of the case studies that I will show later. So it's called IMACLIM-R model. It's a multi-region, multi-sector model of the world economy that represents the intertwined evolution of technical system, energy demand behaviors, and the macroeconomy. It combines a computable general equilibrium framework with bottom-up sectoral modules in a hybrid architecture. It's a recursive dynamic model. It represents endogenously GDP and its structure. It represents also the evolution of energy markets, prices, energy shares in the different sectors, technology choices, induced technical change, and of course, CO2 emissions. And the main exogenous assumptions that we use are the evolution in population, in labor productivity, the maximum potential of technologies, for example, renewable, carbon capture and storage, the learning rates, decreasing the cost of the technologies, some assumption on fossil fuel reserves, the parameters of the functions that represent the induced energy efficiency, because energy efficiency answers to price that are endogenous, and also parameters representing the energy demand behaviors and the lifestyle evolution, for example, motorization rates, residential space, the evolutions and consumption preferences, etc. And another way that is maybe less usual to represent the model would be like this, with the endogenous variable in the middle circles, so the ones that evolve, or the evolution is represented and represent the relationships between the cost of CO2 abatement, CO2 emission, GDP, final demand by sector, etc. Then in the second circle, we have the exogenous trends that are assumed and that we can vary per scenario. So these are, for example, the population evolution, the labor productivity evolution, the emission coefficients, things like that. And the outer space is the emitted elements. There are many more than the ones that are here on the slide, but the notable ones like climate change damages are in the default version of the model emitted. We are working on representing, like integrating that now. Other things like debt and money are not represented. The income distribution within country is not represented. Conflicts, war, governance in general is not represented, and it's probably extremely important for the evolution of the system that we are modeling. So with this introduction, now I'll go with the case studies, if that's okay. Okay, don't hesitate. If you have questions or want to make comments, you feel free to interrupt. So the first one, it's an example with both scientific and ethical uncertainty. It's not with the Maclim model, it's with another IAM that we're also developing and using at CIRED. It doesn't have a name. It's a stylized CBA IAM, so a dice type, but where we add some elements, and in particular stochastic damage, so real uncertainty in the realization of damages. And there's one article that we use that IAM to ask the question of how the possibility of a tipping point and impacts from climate change can influence the social cost of carbon. Indeed, we know that there can be some threshold effect and some non-linearity that are triggered when we explore warmer climates, for example, the dieback of the Amazon forest. And this kind of phenomena is usually referred to as climate tipping point. So it's been shown in the literature that including tipping points does increase the social cost of carbon. But the existing studies, well, before that paper, did not disentangle how this increase in the social cost was coming from an increase in the expected damage and how much was coming from the pure stochasticity, the pure risk effect of the presence of a tipping point. So we tried to investigate that issue. So we model a tipping point as a stochastic risk that triggers a shift in damage, leading to a higher damage regime after a tipping point is crossed. And we do two things to isolate the effect of pure risk. First, we disentangle the preference regarding risk in time in the social choice framework we use. So the usual social choice framework is probably, well, the most classical is the one with constant relative risk aversion. So where, in fact, the resistance to intertemporal substitution and the risk aversion is the same. And it's in this theta parameter of the utility function. But we know that the resistance of intertemporal substitution and the risk aversion can have opposite effects in the presence of risk, because resistance to intertemporal substitution will favor the consumption of present generations, and the risk aversion will encourage more abatement in the present to lower the risk for the future. So that's why we need another social choice framework to disentangle both. One framework that does that is the Epstein preference social welfare function, where you have two different parameters. So you have like this theta here that does represent the resistance to intertemporal substitution, and you have the gamma parameter that represents the risk aversion. And so the results that I will show will be with that Epstein social choice welfare function. And the second thing we do is that we, in the results that we'll look at, will control for expected damage. So how we represent damage. So before the tipping point, we had the usual damage parameter, the dice type. And after the tipping point is reached, it adds a J increase in the level of damage. So it's like going from that damage function to that one if the J is equal to 50%. If it's equal to 10%, it's going here. And at each period of time, there's a probability, a hazard rate H, that the probability is reached. And the hazard depends on the temperature. It's increasing with temperature, such that the expected damage is the dashed curve. So here in the case of J equal to 50%, and here in the case where it's 10. And what we'll do is to run twice the setting, one with the stochastic tipping point and computing the social cost of carbon like this, and then you making a second run with the damage set to the expected damage and with no uncertainty, and computing the social cost of carbon under the expected damage that we'll call the SCC-ED, expected damage. And so the SCC and the stochastic setting represents the full effect of the tipping point. The SCC-ED will represent the level effect of the tipping point, the more damage and absent of risk. And the difference between the two is the pure effect of risk. So these are the results. So here you have like the heat map of the social cost of carbon, the absolute value in the case of a stochastic tipping point. But what's more interesting is looking at the ratio between the social cost of carbon in the case of deterministic expected damage and the social cost of carbon with the stochastic tipping point. And so that's the share. So if you are here, it means that only 10% of the total social cost of carbon is explained by higher expected damage. If you are here, that one is 90%. So it means only the risk only adds 10% to the social cost of carbon. So what we find is that the stochastic risk has a strong effect on the social cost of carbon only when the risk aversion parameter is high and when the risk itself is high. Well, it's sort of obvious.
That you are looking at, are these socially optimal runs?
Yes, they are.
Are these standard scenarios that you could do?
No, socially optimal.
So it is already reducing the emissions when you have the tipping point included.
Yes.
Okay, that's good.
Wondering how do you decide the probability of the tipping point?
Ad hoc.
Okay.
Yeah, it's we represent it like this. So it's between two temperatures. So after a max temperature, we can vary the max temperature, let's say above 5. Well, this figure is for 7. So above 7, for sure, you'll reach it. Below 1 degree, you don't. There's a 0 probability, and in between, it's increasing. So if you would have stopped before 1 degree, you would never have a risk to have a tipping point. If you mitigate to remain below 2 degrees, you have every year some risk to trigger the tipping point. And if you continue to increase warming, that risk increases. Yeah.
But you seem to use a very low damage function. Oh yes.
Well, it looks like you use a very low damage function, the default one, but if you use a higher damage function, then your optimal run would already mitigate much more, then you would never reach these tipping points. So it kind of has a big effect on it, right?
No, true. We're using the dice default.
But would it be still significant if we use a different damage function?
Well, it would depend on how big the additional damage you would have. Exactly. So, yeah. But if you would use a deterministic damage function that already makes mitigation to 1.5 degree optimal, then the difference would be smaller, for sure. Yeah. Well, we tried to find typical values in the literature, and they're big ranges. So like some papers sort of explore rather here, so in between 1 and 5, but some also go to 20. So we're a bit agnostic on that, and we're.
What does it again? Is the higher risk aversion
is 20 is higher risk.
So then you want less risk.
Exactly.
Yeah.
So I mean, the result, the direction of the result is obvious. The only thing we can do is to quantify it. And I mean, there's not much more that we can do except exploring the implication of using different parameter values and different forms, and yeah, that's what we can do. So it might also be why we would like to study directly with more detail the mitigation pathways, abstracting from the uncertainty about damages, and that's what we'll do now. So in the two next examples that take into account multiple uncertainties on growth, on future technologies, on fossil fuel reserves, etc., for the construction of socioeconomic scenarios, for the analysis of emission trajectories and emission reduction policies. And the aim of the study is to highlight the uncertainties that matter, maybe the salient uncertainties, or like the main determinants of a given outcome of interest. So the research questions that we ask are: which uncertain factors had the most influence on the results, or in which cases, in which combination of uncertain factors, we have some specific outcome that is interesting, either because it's desirable or because it's undesirable. So yeah, like having an output variable that is below or above a threshold, for example, a temperature threshold, but it could be also above a poverty threshold, or some levels of some indicators that are considered critical or desirable, depending on the question. And to answer those questions, we construct a structured ensemble of scenarios by combining systematically discrete seats of parameter variance. So that's with the McLemore model, and then we analyze the ensemble to highlight which uncertain factors are important. So we do a global sensitivity analysis, or we use a scenario discovery approach to try to uncover which combination of assumption lead to a specific outcome that we are interested in. So to construct the ensemble of scenarios, we start from what we think could be the potential drivers of the outcome of interest. we like the set of parameters that might matter for the results. We make several groups, for example, some like 7, and we systematically combine alternative variants for values of this parameter sets. Thus, we build we run all the combinations and build a database of scenarios, potentially a large one, depending on the numbers of variants and numbers of groups of parameters. In the examples that I show later, where we sort of study the link between economic growth and CO2 emissions, we identified 7 groups of parameters of the IMACLIM model that potentially matter for the results. So productivity growth, availability of fossil fuels, the parameters representing energy demand behavior, the parameters representing energy efficiency, the parameters representing the cost and potentials of lower carbon technologies, and the representation of labor markets. And we made 2 or 3 variants for each and combined all, thus running 432 times the models, and that gives 432 baseline scenarios, so scenarios without climate policies. And these are the sort of results that we get, some spaghetti graphs for some output variables like GDP per capita and CO2 emissions, for example. In the first paper, the question was what combinations of factors may lead to high emissions. So here in this graph, you have like each dot is a scenario represented by its per capita GDP in 2100 and its cumulative CO2 emissions. And we do find that there are cases where the growth is not so fast and we have high emissions. And these are cases that might be important for policymaking, because these are cases where challenges for adaptation, for example, are probably bigger because you have high emissions and less capacity to cope. No, it doesn't. So to go back to the combinations of the uncertain parameters that lead to high emissions, we use what we call a scenario discovery algorithm. It's called PRIM. And you have here the link to a GitHub repository for a Python package that implements that algorithm and others as well. And what it does is that it investigates like all the combinations of factors and finds which are predictive of being in that box and not being outside the box. And in this case, it finds 4 scenario families that you have like in the 4 colors here. And so 4 combinations of drivers. For example, the cases with high emissions but relatively low growth here. So in blue and yellow, with the blue being the combination of high availability of fossil fuels, energy intensive demand behavior, and low to moderate productivity growth, in conjunction with low availability of, so low potential and high cost of low carbon technologies. That's for the blue family, and in combination with slow energy efficiency for the yellow one. So yeah, that's one case. So a second example is builds on this ensemble of scenario, but adds some mitigation policy. to meet a given emission pathway in each case. So for the 400 something baseline, we add mitigation policies to reach the same emission pathway with two variants of the use of the carbon tax, that is either given back to households or used to reduce pre-existing taxes, and that makes double the number of mitigation scenarios. And so another application that is not published and might never be published, it's okay, that happens. We analyzed which factors influence most the mitigation costs. So the GDP variation in between the mitigation pathway and the corresponding baseline scenario. And also a second indicator, the absolute growth in the mitigation pathway. So each circle is again one mitigation scenario. So plotted against its GDP loss compared to the baseline. So that's usually what we call the macroeconomic cost of mitigation, and that's usually what is summarized in IPCC reports, for example. And the other axis is the absolute level of per capita GDP that is reached in the mitigation scenario. And it's expressed as an index of the mean across all scenarios. And what we do is that we use a classification and regression tree that is called CART. You also have the same GitHub repository with the implementation as a Python package. So, and this algorithm identifies the main drivers for the outcome, the metrics that we are interested in. It's actually based on successive analysis of variance to find the dichotomous split of the drivers that yield the strongest possible production of the metric at each step. And then, so at the top node is for the whole ensemble of scenario, and then it's for half of it. And again, so at the, for example, at the first higher level, we find that GDP losses are mostly determined by the way the carbon tax revenue is redistributed. And then if it's redistributed to household, the macroeconomic loss is higher. And it's at the second step, it's higher if low carbon technologies are expensive and their potential are low. And in the other case, the second important driver is the availability of fossil fuels, with low availability of fossil fuel leading to low macroeconomic cost of mitigation, because the low availability of fossil fuel is making baseline scenarios grow less because energy prices are higher. But if we look at the main drivers of the absolute level of per capita GDP in mitigation scenario, the main drivers are different. They are the energy demand behaviors and the energy efficiency speed that are the main determining factors for this indicator. So this result is potentially important because the aim is not to reduce emissions under some economic constraint, but to find development models that are compatible with carbon neutrality. And so the analysis is, we should focus on that second indicator. And what we find is that what matters, the levers are potentially different, and we might put more emphasis on those and maybe less on the technologies and on the carbon tax recycling topic. Okay, so until now, we saw examples with only one model. So we did not explore structural uncertainty, like model uncertainty. So I want to show you two examples with several models, one with a few and one with many scenarios. So the first one, it's an article that explores the key drivers of future CO2 emissions in a multimodal setting. So with 6 different IAMs that have different structures. And one of the difficulty when you have a multimodal setting can be the computational cost for some of the models. So what the paper did is to use a parsimonious approach to have only a few model runs. So in that case, because we were exploring population, income, energy efficiency, fossil fuel availability, and low carbon energy technology development. So that's 5 sets of parameters. We needed only 23 model runs per model, which is quite parsimonious. And the method also, contrary to a one factor at a time type of sensitivity analysis, and if you vary only one factor at a time, you only have like the individual effect of the factor, but you don't have like the interaction effects between the different factors. The method that we used is precisely able to capture the interaction effects between the factors. It does so by changing like the factor from a reference to an alternative value, but also running the case where we change all of the other factors but this one. And so that way we can have like the individual effect in the first case and the interaction effect in the other case. And with the two, we can compute the total effect. So yeah, it's the sort of results that we get are shown in this panel that shows the results. So the percentage change in cumulative CO2 emissions when parameters are changed to like from the values they have in an SSP2 setting to the value they have in an SSP1 setting. So, and the different colors are the different models. So for all models, the total effect is a reduction of emissions, and the main factors are the GDP per capita and the energy end use parameters that act in the different direction, and for both the interaction effects, which are the sort of lighter part of the bar. So the individual effect is that part, and the total effect is this part. So in this case, for example, the interaction effect reduces the individual effect. And yeah, I probably don't have time to explain what is behind this result, but if you would want to, you could read the paper. So the second paper that I wanted to talk about is one that looks at the prospect for future inequality between countries under climate change. So you probably know that we're in a context where the inequality between countries has been decreasing like for several decades now, that they are still the main factor explaining the global inequalities, even though the inequality within country is increasing and might at some point become the main driver of global inequalities. And it's the inequality here is measured by the Gini index. So the higher the Gini index, the higher the inequality, and the lower inequality. And the question is, how could it evolve in a future warming world? Actually, the declining trend could be reversed, because we know that climate damages are disproportionately affecting the countries that are poorer. So that is an exacerbating factor for inequalities. And for mitigation, the effect is a priori ambiguous, because it reduces damages. It would reduce inequality between countries, but the cost of reducing emissions may also, depending on how the policies are designed and implemented globally, and the burden sharing and the financing is organized, it could also potentially increase inequality, and depending on which effect dominates, climate change mitigation policies could reduce or increase inequality. So in the article, we wanted to know that. And to answer the question, we considered the available projection and the associated uncertainty along 3 dimensions. So the socioeconomic development, the convergence between countries, like the trends and demographics, socioeconomic, education, technical progress, general technical progress in the various countries. Also, the available estimation of the impacts of climate change and how they are distributed across countries, and the estimation of the economic cost of mitigation, the macroeconomic implications of investing in low carbon solutions and structural change away from emitting activities, and how these are also distributed across countries. So we combined all those estimates in a common framework, starting from the 5 SSPs that you know, I guess. So that are 5 shared illustrative pathways of some contrasting assumptions about demographic evolution, education, economic growth, etc. And then from the SSP database, we also take the mitigation costs to reach the various RCP levels from the 4 models in the SSP database that give the macroeconomic cost of mitigation. And because it's only at the regional level, we also have to add some assumptions of how it's distributed within the regions that are the model regions. Then we combine these with the existing estimates of temperature change caused by the RCPs. And because it's a little old paper, it's on CMAP 5 results. And we also combine with the existing, well, some existing estimates of the economic impacts of climate change coming from several studies, and using 8 damage functions, either from some IAM type of studies or some econometric-based studies. And to give you a range, what we use ranges from below 2% to about 20% of global GDP loss for a 2-degree warming in the alternative functions that we're using. So combining all these, we have 3,000 something scenarios that project GDP and GDP per capita for almost all countries of the world, and we can compute the Gini coefficient between the inequality between countries in all those scenarios. And these are the results. So it's the evolution in the Gini index over the century for the 5 SSPs, And here we highlight the highest damage case in red and the lowest damage case in blue. And of course, in the highest damage case, the other parameters uncertainty are more important because they're magnified by the damage. And we can also analyze which, like with the same scenario discovery algorithm, like the PRIM one that I talked about, in which cases the trend of inequality reduction is reversed over the course of the century. And this is what we find. So we find that there are cases of trend reversal, so cases where the inequalities between countries start to increase again in this century. In all SSP cases, even the most optimistic one, but that happens when the damage are high. And we also find that there are cases for all damage estimates, in particular in the case of the SSP4 that is called inequality. So yeah, that is again something that was expected. And we can also study the drivers of future inequality. So with the same type of regression tree analysis that I showed in a previous example. And what we find here is that the socioeconomic assumptions and the damage are the main determinants of future inequality. We also find that well, the emission trajectory and the mitigation trajectory is important. And in particular that the lowest emission scenarios are the ones with the lowest level of inequality. Yeah. So I also wanted to mention that article. So if you want more examples of articles that are using ensembles of scenarios, here is a recent perspective paper that reviews the example, but also identified key methodological challenges to do so when some existing methods and to address those challenges. And it proposes, well, a three-step approach to pre-processed ensemble, to either, for some cases where what you're interested in is selecting a few scenarios from that ensemble for sequential analysis. There are some methods and also methods to analyze the full ensembles, which are more what I showed you today. And something that's important also, and we need probably to spend more time and more efforts to provide the users with good access to the information and good communication of those uncertainties. So to conclude, I would like to say two words. The first one is humility. Okay, models, scenarios, we will be wrong. We know that. We know that we have a long track record of wrong scenarios. We know that what we're doing is not forecasting. We are exploring the uncertainty, but our results will be compared to actual observation as time evolves. And we will be wrong. It's okay. Sometimes it will be in the range of what we will have explored. But here you have some cases of, well, you can look at the papers if you want, but even with a high range of uncertainty, the actual number is below. So yeah, the only thing we can do is face it, be humble, be careful with our results, and remember that although what we do is designed to explore the uncertainty space, the possibility space, even with large ensembles of scenarios, we will not fully or equally explore that space. And it's how it is. But on the other side of that humility coin, there is the responsibility we have, because the model results can and do inform and influence decisions, such that the modeling decisions that we make may narrow or broaden the content of the policy debate, and maybe studying certain types of scenarios, certain types of mitigation options, certain types of technologies or policies, or certain types of questions even, may very well make them more, I would say more, maybe in some cases less, more feasible, more desirable, more probable. And so, yeah, what we're doing is not neutral. So in that context, we have to ponder the tension between excluding some scenarios, some options, some questions that we would judge inappropriate, or maybe less probable or less plausible even, and maybe the risk of missing some type of low probability, high risk type of scenario, or those that represent some discontinuities, some surprises that might be critical for analyzing the risk and the vulnerability of decisions and strategies that we're trying to inform. So we also have to be very mindful of the way we communicate uncertainty, and that is very tricky. Ideally, what we would like to do is to highlight the results that are robust to the uncertainty that we could cover, but also state the ones that we did not cover, or maybe highlight the key factors that do influence the results. But it's very tricky, and I think we have to navigate between Scylla and Charybdis. So between the risk of giving a false impression of precision and giving overconfidence in the results, and also the risk of giving a false impression of ignorance that might delay or even deter action, especially in the context of climate change, where we know that some lobbies are manipulating or fabricating uncertainty and using that to lobby against action or to delay meaningful action. So it's an important topic. And I would say sometimes as scientists, we overemphasize uncertainty. And so we really have to think and adapt to our audiences and the various audiences that we have, and probably to also have like a scientific approach to that, to test and evaluate our communication and visualization tools and choices with what it produces in the audience. So to finish, one last example that did exactly that. It empirically evaluated how a figure displaying the temperature outcome from a range of scenario. So that's from the IPCC 4th assessment report, how it was understood by the target audience policymakers. And what the paper found is that the readers were unable to identify the two different types of uncertainty in this graph. So the climate model uncertainty and the emission scenario uncertainty. And so they saw a great deal of uncertainty and falsely attributed it to the climate models. And so overestimated the uncertainty in our knowledge and underestimated the importance of the choices and the socioeconomic choices of mitigation action that we can make. So this is a very important result. And in the 6th assessment report, there was an attempt to make the figure that shows exactly the same information, but just with the updated knowledge, easier to interpret. So here it is. What it does, it gives explicit names to the scenario, the emission scenarios with very high, intermediate, very low. It adds climate uncertainty only for 2 of them. It adds some text to try to guide the reader to understand the figure. And there's also another panel in the synthesis report that displays almost the same information in a different way, using the now famous climate stripes for the same 5 emission scenarios, and adding some human icons to make it more personal. So I think it will be important to test empirically how if that works better or not. And yeah, so now it's time for your comments, questions, remarks.
Yeah, thanks a lot, Celine. Great insights from a wide range of angles, from the uncertainties, the model, responsibility also to the communication. Yeah, a really wide range of topics, I think. Yes, so we have 10 minutes of questions and answers in case. You also already highlighted the important question of visualization and then interpretation. Also links, of course, well to Kai's talk after the coffee break on that. Yeah, please think about questions. I will pass it around. If I may continue my list of M words of this summer school, I mean, we started with mass, money, and morale in the energy modeling by Nico, the markets in the CGE model. Maybe now this is about the modesty of modelers also. I mean, your responsibility to do it right. And then we go, maybe you can think of one, matplotlib, maybe, I don't know. You can find a nicer one, maybe. Anyway, yeah, I don't know if there's any questions or reactions immediately. I'm sure there are many. Okay, let's just please use the mic for eternity. You know.
Thank you very much for the great presentation. I have a question regarding the use of a card for kind of like exploring the main drivers. Which I've never seen it before. I found it super interesting. My question was, a card as a prediction method is a single tree is quite unstable, right? With a high level of variance. So did you also see that in your results, or is there also a way to kind of like circumvent that to some extent? Because I think it's a great way to interpret and visualize what drives the results. I was just curious how stable it is if you use a single tree.
Okay. So no, it's not stable in the sense that at each step, it really takes the one driver that is the most predictive so explains the most variance of the result. And 2 drivers can be quite close. And you see it here. For example, I told you that for the absolute GDP, energy behavior driver was the most important. But what you see is that if you look at that dot and that one, the difference, this one is a little bit higher, but this one is just a little bit lower. So in fact, the way you use the carbon tax revenue is also important. And CART doesn't show that. But you can use other, like the total analysis of variance that will show you the individual effects and the interaction effects. A little bit like the very first figure that I showed you, where the contribution of uncertainty from the internal variability, the model, the climate model uncertainty, and the emission uncertainty did. So you can also like analyze the contribution to the total variance of the different factors. And on that, you would see that some are quite close. You wouldn't have that sort of dichotomous effect.
I was wondering to, waiting for the plane.
Maybe wait.
Okay, I was wondering to which extent you think that there's a bias in IAMs because of the fact that some things are easier to measure and to model than others, and those are included and others not. Because some processes are just very, very hard to model, especially when it comes to behavior or societal responses. And if so, how to deal with that? As in, like, obviously trying to improve the models is one way, but also like some things are very hard to conceive that they ever will be properly modeled. So then we have to, I guess, like adapt communication, or what's your view on this type of uncertainty?
Good question. Well, probably there's a tendency to do first what is the easiest to integrate. But I also think that the community is mindful of the social demands to explore also things that are important, but maybe less easy to model. How to deal with that? Maybe it's also like some choices of the design of the research questions that we ask, and also the design of the funding calls that we reply to, and also trying to influence those to put some emphasis on the things that we think that matter but might be more difficult. And then I think we have to be transparent about what we know, what we do, what is in the model, what is not, and how, if we can, how we think it would change the results. Sometimes other types of models can help, and working with communities that have the experience with those other types of models can be a good idea. Sometimes some more qualitative analysis can also be a complement. And then on the communication, it's very tricky because you don't want to overemphasize the uncertainty, as I said, but you also want to be as transparent as possible. So I would say try to adapt to who you are talking to. Yeah.
Okay. Yeah, thanks.
Yes, thank you. I think it was very impressive how you showed like all the different parameters, values that you're like exploring in all these studies. I was wondering whether another underlying reason of that uncertainty we have in parameter values and in functional forms and model structures is that our models are so aggregate in terms of the spatial scale, temporal scale, sectoral scale. And while, for example, risk aversion parameters, there's like empirical studies showing it just differs a lot across countries or like income groups. And whether like a way forward for our modeling is also to improve our scales of our models, like, and that way reduce uncertainty just by more accurately perfecting, yeah, subnational and like household groups and like temporal scale, like annual mechanisms, like those type of things. Or what do you think?
Well, for sure, looking at finer scale analysis is important, and all the more as like decisions are taken, like most of the decisions are taken at the national or even a more local scale, and it's important to also have some elements for like the policymakers at that scale. I'm not totally sure it's a task for global IAMs. It might be a task for national models. And on the relationship to uncertainty, I don't know. For sure, it reduces the uncertainty on data, for example, because you can use like well, at least for the countries where you do have some good quality data. But sometimes it can also increase the uncertainty because you add some mechanisms, and so that adds some uncertainty. So on the relationship with uncertainty, I think it can go in both directions. But in any case, it is important to also have some analysis that is more local. And even like for global studies, if we want to be relevant on the topic of inequality, for example, we have to account for within regions inequality. So, yeah.
Yeah, thanks. Good points. I don't know if there's any other further question. We have a coffee break. Maybe just one comment, if I may, since I have a microphone on the last two questions, which I think are very good. On the last one, yeah, on the spatial scales, I mean, I think improving scales of many models is a big effort and definitely important for many dynamics on policy making, but also on welfare, etc. So, and I mean, also Celine, I mean, you've been working a lot on, for instance, the papers you showed on inequality. I mean, like 5 years ago, that was not considered beyond the national or sub-regional level. So there's been a lot of work, and I think this really shows how these models are moving ahead, and how also like what are potential research topics to work on. And maybe to Felix's point before on these kind of features that are not captured, I agree they're important, and you mentioned it also. Uncertainty is of course huge, but also if you look at some recent publications, there are a lot of people working on the behavioral factors, political factors, institutional factors. They're very hard to model, but so if you were the first one to give it at least a try, it can be very useful, important, and also very nice because you can publish it very importantly because no one has done it so far. It's also, that's why we in the group work, we said we try to strive for innovative thoughts, because in the end, it's also from a personal perspective, can be nice because it gives you an edge and you can really be kind of one of the first to do this kind of things, which I think, yeah, it's maybe easier in some sense than just, you know, do an epsilon on something already existing where hundreds of researchers have worked on. So I think, yeah, it's always good to try some innovative things like we try with the group work as well. Yes, but I don't know, any further comments? Yeah, feel free to reach out to Celine. Also, she's very happy to answer any questions, and maybe